Hello friends, I welcome you all to my channel. This video is part of the playlist Mathematics Class 11 where I upload videos on all the chapters. Uh, this video belongs to the playlist Mathematics Class 11 Limits where I upload videos on finding limits. Uh, so I've already uploaded many videos on limits. Please check out the playlist Maths 11 Limits uh, to understand all the methods of finding limits I've already discussed. In this video, I will discuss how to use the standard results to find limits of exponential and logarithmic functions. Before I get started, I will highly request those of you are watching my videos on on limits or for class 11 mathematics, please support me by subscribing to my channel, like the videos, share the videos with your friends, and also do not forget to press the bell icon so that you will be notified by my future videos, as I will be uploading more videos on limits for class 11 in the future as and when required. So let's get started with this video. Okay, so on the to find limits of exponential and logarithmic functions, it is often very handy to know to use the expansion series of some logarithmic and exponential functions. Those series I have as a reference, I have uh, taken. I have as a reference. I have taken as a. You can see on the left hand side, I have the series expansion series of the standard logarithmic and exponential expansion that could be used while solving the limits of exponential and logarithmic functions. But using these expansion series may not be it may not be allowed for uh, in your board exams. So be careful about it. But definitely for competitive examination, you can always use this expansion series, as they are very handy and they minimize the computation limit a lot. So for the exponential and logarithmic functions, the standard results, we basically have primarily have two standard results. The first one is uh, limit x tending to 0 a to the power x minus 1 divided by x is log of EA, where we must have a greater than 0 and a not equals to 1. Now, this is the standard result, but please note that this result can also be applied if instead of x we have any function of x, but that in the power of x, in the power of a, and that same function of x has to be in the denominator. So this is a special form. A more general form is the a more general form of the standard result is uh, limit x tending to a. Sorry, let's not take a because we already have a. Let's say limit x tending to c, some constant, uh, a to the power fx minus 1 divided by fx is also log e, provided we have where limit x tending to c fx is 0. So if you have the form a to the power fx minus 1 divided by fx for some x tending to c, it will be log a to the base e if we see that limit of fx when x tending to c is coming out to be 0. So this is the first one. The second one, now you can see that if you have this is for a general any constant a. If you now if you have e instead of a, you can see that the result becomes log e which is 1. So just a note that limit x tending to 0 e to the power x minus x is 1. Also, uh, also for this general form, we can see that uh, we can have e to the power fx minus 1 by is 1 if limit x tending to c fx is 0. Now, this is the first result. The second result is uh, limit x tending to 0 log a 1 plus x divided by x is uh, this is log a e, log e to the base a. So where here we have the log to the base a. So the result is this. So this is the special form. A more general form again is uh, limit x tending to c log a 1 plus fx divided by fx equals to log a e if limit x tending to c fx is 0. Now in the if we substitute again e, if a is if in the limit we are given e instead of a, we can see that limit x tending to 0 log of e 1 plus x divided by x is 1. Also, uh, also you see log of e fx, this is also 1 if limit fx is 0. So third and the last result is limit x tending to 0 1 plus x to the power 1 by x is 1. This is the special form. And the general form is is limit x tending to c 1 plus fx to the power 1 by fx is 1 if we have limit x tending to c fx equals to 0. So these are the standard results that we will apply for solving problems on exponential and logarithmic functions. Now, uh, a general a general strategy for solving this kind of limits is that if we are given a function where we see okay, let's try to solve some problems and then we will discuss and understand the strategy. Let's solve some problems. Uh, so, example 1, say limit x tending to 0, 3 to the power x minus 2 to the power x divided by 10x. Now, the general, we see that we have two exponential terms, 3 to the power x and 2 to the power x. Uh, the general strategy is that whenever we see a part of the standard result, we try to complete that standard result by adding some term, adding some factor, and then adjusting that factor appropriately. So over here, we can see we have 3 to the power x and 2 to the power x. So uh, it will be a general tendency to, it would be nice if we can somehow make, if we can somehow have 3 to the power x minus 1 and 2 to the power x minus 1, but then we need x in the denominator. So what usually we do to solve this kind of problem is that we mm, one way is that we add minus 1 to this, and that 1 can be adjusted if we write 2 to the power x minus 1 this way. So the 1 got adjusted, minus 1 and plus 1. So we are left with 3 to the power x minus 2x and then 10x. For sure, we can understand that to control 10x, to tackle 10x, we need to transform. We need somehow to create the expression 10x by x, and then we will do some adjustment later on so that we can use the limit 10x by x, x tending to 0 is 1. Now, okay, now for 3 to the power x minus 1, we will need an x in the denominator, right? Also for 2 to the power x minus 1, we need an x in the denominator. So let's add the the x in the denominator. But when we have added x in the denominator, we also will have to readjust it by multiplying x in the with the numerator. So now, mm, so now if we break the two limits, we have two terms with minus. So if we separate out the limit like this, 3 to the power x minus 1 and x 10x minus we can do this. We have separate out the terms. So this is, we have written simplified, separate out the terms, and it becomes like this. Now what we do is, we have this 3 to the power x minus 1 x. This is the standard result we got. And then we have over here, we bring the x down, we get 10x by x. Now for this, similarly, we can write it as and we bring the x, this x down to with 10x. Now we can apply, we have all the standard results, we can apply the standard results. So this will become, for 3 to the power x minus 1 by x, it will be log 3. What is the result? Log E3. So this becomes log E3, and of course this becomes 1 minus, over here we have log E2 into this. So this becomes log E3 minus log E2. So and this is log E3 by 2. This is the answer. This was one way of solving the limit. So you must understand there are multiple ways of solving a limit problem. You can use standard result, you can use expansion series, you can use L'Hopital rule if it's in the form of 0 by 0 or infinity by infinity, or you can manipulate the expression, somehow create standard results, and then apply the standard results. Now, this problem, I guess, could have been solved in a little different way. How? What if we take 2 to the power x common in the numerator? If we take 2 to the power x common in the numerator, this let's try it. It's always good to uh, see multiple ways of solving a problem, so that you can apply the method which is takes least time. Let's see if we can solve this in a little a different way. Let's say this is method 1. Let's say limit x tending to 0 let's say method 2. Okay, method 2. What I was thinking, that if I take 2 to the power x common, from here what we get is 3 to the power x by 2 to the power x, and over here minus 1. And see, the the thing is, if I take 2 to the power x common, I will get a minus 1, and over here I will get some constant to the power x, and this factor 2 to the power x will not cause any problem, because this 2 to the power x will eventually be 1 when x tending to 0. Okay, so let's put okay, so now this becomes 2 to the power x, and this is 3 by 2 to the power x minus 1, and we have here tan x, but I would like to have x here so that I can use the standard result a to the power x minus 1 by x, where over here a is 3 by 2. So I will add an x here, tan x, and I will adjust this x by writing this. So now uh, this is 2 to the power x. Over here we have x, and over here we have so we can apply tan x by x equal will be 1, and this, okay. So let's now apply the standard result and substitute the value of x tending to 0. We get 2 to the power 0, and this will become log e 3 by 2 into 1. So this becomes eventually log e 3 by 2. So we got the same answer. Now you can see which method is took less amount of time, which was the shorter method. More or less same, but just it is good to have to know various methods to solve a problem. Okay, let's see the next problem. The next problem is limit x tending to 0, 5 to the power x plus 3 to the power x plus 2 to the power x minus 3 divided by x. So we can see the a to the power x terms in the numerator, a lot of a to the power x terms in the numerator, and we already have the x in the denominator. So somehow if we can create the terms a to the power x minus 1 in the numerator, then we can separate out. See, where we can see minus 3. So we can distribute the minus 3 with all the a to the power x terms, and we can write this as, what we do is we distribute 1 minus 1 with 5 to the power x, we distribute minus 1 with this, and 2 to the power x minus 1 x. So now clearly we can separate out the terms, and we see this plus limit 3 to the power x minus x plus limit x tending to 0, 2 to the power x minus 1 by x. So now we can apply the standard result of a to the power x minus 1 by x, x tending to 0 is log a. We can see this is log e 5 plus log e 3 plus log e 2. This is log 5 into 3 into 2, that is log e 30. That is log e 30 is the answer. Okay, so whenever you see a to the power x in the numerator, always try to create the a to the power x minus 1 and somehow then readjust the other terms, and so that we can apply the standard result a to the power x minus 1 by x when x tending to 0. But in some cases it may not be always be x a to the power x, it could be some other function of x, but that function of x could be tending to 0 when x tending to 0. So in that scenario we will apply the general form. Let's proceed with the next problem. Problem 3 is uh, limit x tending to 0 a to the power mx minus b to the power nx divided by x. Now you can see the term a to the power mx. Now it has mx, it is not x anymore. But when x tending to 0, we can see that mx is also tending to 0. So also we need the minus 1 term. So we can always add minus 1 with this one, and we are readjust that minus 1 by writing the b to the power nx minus 1. So 1 got adjusted. Okay. Now fine. So if we separate out the terms, if we distribute the limit over the terms, we get mx minus 1 by x minus limit x tending to 0 b to the power nx minus 1 by x. But we need, for the first limit, we need mx in the numerator, in the denominator, and for the second limit, we need nx in the denominator. Only then we can apply the standard result. So why not create mx for the first limit? Why not we create that mx and we adjust it? And similarly over here we have b to the power nx, so we need nx, and then we adjust the n. So now this becomes the m 1 by m goes to the numerator, and it's a constant, we can take it out, and we have limit m into limit x tends to 0 a to the power mx minus 1 by mx, and over here we have n limit x tending to 0 b to the power nx minus 1 nx. Now now we can apply the standard result because we have mx a to the power mx, and that same mx we have in the denominator. Also in the second limit we have b to the power nx, we also have nx in the denominator. So this becomes m log e a minus n log e b. Mm, uh, okay. See, if if we do a little bit of simplification, we bring the we write it as a to the power m and a b to the power n. Simplify it to give a compact single term. This becomes a to the power m by b to the power n. So this is the answer. This is the answer. Okay. So let's see the next problem. The next problem is limit x tending to 0 e to the power 2x minus e to the power x divided by sine 2x. So I guess this problem looks similar to the first problem we did. This one, we have two terms, a to the power x minus 2 to the power x, and we have some term in the denominator, but in the numerator we have a to the power x minus some two terms a to the power x. Here also we have similarly two terms a to the power x. So what we can do is we let's bring e to the power x common from the numerator, and we get e to the power x divided by e to the power x minus 1, and over here we have sine 2x. Now this is e to the power 2x by what mm, 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 mm. Okay, so this becomes e to the power x minus 1. So, and we have sine 2x. Now we have the e to the power x minus 1. We just need an x in the denominator to have the standard, so that we can apply the standard result. So we create that. We create that x, and then we adjust that x by multiplying with the x over here. Now for sine 2x we need 2x in the denominator, but we have x. So what we do is we put sine 2x over here, and then we adjust the two like this. We already have sine 2x by x, but we need 2x, sine 2x by 2x. So we wrote, we added the 2x and we multiplied by 2. So it gets adjusted. Now, if we rearrange the terms, we get over here this thing, and sine 2x by 2x multiplied by 2. Now we can apply the standard result, and it becomes e to the power 0. This becomes 1, and this becomes 1, and this is 2. So this is half. Half is the answer. Okay, let's see the next problem. Problem number 5 is limit x tending to 0 e to the power sine x minus 1 divided by x. Now you can see we have a to the power x, but instead of x we have sine x, but that sine x is also tends to 0 when x is tending to 0. So what we do is we create the standard result. We have sine x over here, and we will write sine x over here to form the standard result, and then we will adjust the sine x, and over here we already have x. So this becomes straightforward. Now we can apply the standard result of TTP power x minus 1 by x, and this is 1, this is 1, and this is also become 1. So 1 into 1, 1 is the answer. This was simple. Okay. Let's see the next problem. Uh, limit x tending to 0 log of mod 1 plus x cube divided by sine cube x. Okay, we have mod. Why there is mod? Because x is tending to 0. So if x is 0 plus, then we won't have any problem, because 1 plus x cube will be uh, the argument of log has to be greater than 0. So the 1 plus x cube, is it x tending to 0? Okay. Hmm, x tending to 0. Uh, Mod. So we know the standard result log of 1 plus x by x tending to 0 is 1. Is 1, yeah. Because over here it is log e. We know the standard result. Hmm, log of log of e 1 plus x by x equals to 1. But over here we have 1 plus mod of 1 plus x's cube. Uh, we have x's cube. Hmm. So mm, x tending to 0. When why there is a mod? Uh, mod mod of this. Hmm. Hmm. Oh, mod of 1 plus x cube. We have x cube instead of x tending to 0. How do we get rid of this mod? Hmm, mod. When x is tending to 0, when x is tending to 0, then 1 plus x's cube will definitely, if x is tending to 0 positive, it will be greater than 1 plus x cube will be greater than 1. But if it is less than 0, 0 minus, then 1 plus x cube will be uh, a little less than 1. Hmm, less than 1. Hmm, greater than less than 1. Hmm, sine cube x. Hmm, if we rewrite this as log 1 plus x cube and we bring x cube here, and of course we have to adjust the x cube here. So this sine cube x and the x cube, we can merge that by as sin x by x whole to the power cube, and we can put it the standard result 1. But can we say that log of 1 plus x cube by x cube is 1? Mm, mm, uh, mm, extending to 0. Mm, if there was no mod, we would see that the answer is 1. But we have mod of 1 plus x cube. Uh, what is the purpose of giving the mod? Because if x tending to 0, then mm, if x tending to 0, anyway the mod of 1 plus x cube will be 1 plus x cube, because 1 plus x cube will always be positive when x is tending to 0. Hmm, mod square. Hmm. Uh, if we so we have log e 1 plus this, and then we have sin x by x cube. This is 1 for sure, but can we say this is also 1? Essentially, my question is whether uh, limit x tending to 0 log of mod 1 plus x by x equals to 1. Uh, can we say this? Question mark. Can we have this? We know log of 1 plus x by x extending to 0 is 1, but log of mod of 1 plus x by x equals to 1. Mm, mod. Mm. The answer is definitely not 1. The answer says, mm, okay, so the answer is 1. The answer is indeed 1. So when x is tending to 0, 1 plus x cube is definitely greater than 1. So we can easily remove the mod. So we can say that there is no need of the mod. We can open the mod as like this. Uh, Now this is a general form. As you can see, we don't have x, but we have x cube. But x is cube, we also have x cube here. So x is cube tends to 0 when x tends to 0. So we can now apply the standard result. This is 1. So please ignore this. Because we can easily remove the mod, because 1 plus x cube is always greater than 0 when x tending to 0. Okay, let's see the next problem. The next problem says limit x tending to 0 e to the power x minus 1 divided by root over 1 minus cos x. Root over 1 minus cos x. Okay. 1 minus cos 1 minus cos x. We know that 1 minus cos x is 2 sine square x by 2. Uh, so this is e to the power x minus 1, and this becomes 2 sine square x by 2, as we know that 1 minus cos a equals to 2 sine square a by 2. Now we can bring the 1 by root 2 outside, and now we have square root of sine square x by 2. Hmm, Can we say square root of sine square x by 2 is sine x by 2? No, because here x is tending to 0. If when x is tending to 0 plus sine x by 2 will be will be positive, but when x is tending to 0 minus sine x by 2 will be negative. So square root of sine square x by 2, if we bring it outside the root, square root, if we have to say mod of sine uh, sine x by 2, mod of sine x by 2. Okay. Now e to the power x minus 1, we can clearly have x in the denominator, and we can adjust that. 1 by root 2, we can have put the x in the denominator and adjust it in the numerator. This thing is 1 for sure. E to the power x minus 1 by x, the standard result is 1. What about this? We know sine x by x tending to 0 is 1, but we got mod sine. If x tending to 0 positive, we can open this mod simply as sine x by 2. But if this is 0 is if x tends to 0 minus, we have to open it with a minus. And there's a problem. We can the then the limit these limit that x tends to 0 plus and x tends to 0 minus will not be the same. So let's try to find out. Let's see x tending to 0 positive x by mod x by 2 is x tending to 0 positive x by sine x by 2. uh, this we can write 0 positive as 1 by sine x by 2 divided by sine x by 2 into x by 2, and over here we already have the x. So we have put x by 2 in the denominator of sine x by 2 and adjusted it by multiplying it with x by 2, and we already have x in the now this becomes uh, 2. This is 2. Right, so this becomes 2, but x tending to 0 minus x by mod sine x by 2 is actually x minus x by 2, and we can clearly understand that this will be minus 2. So this limit is not existing. Its right hand limit and left hand limit are coming not different. So this limit does not exist, but this exists. This does not exist. This exists. So we can say, so eventually what we are having is that the whole limit, this limit at x tending to 0 plus. Okay, so now let's say limit x tending to 0 plus, the given limit was e to the power x minus 1 root over 1 minus cos x is coming out to be, when 0 plus, this limit is 2, and we have this is actually 1 by 2. No, this thing is 2. This thing is 2. So this will, and we have 1 by root 2 outside. So the whole limit becomes root 2. But also limit x tending to 0 minus the given limit, the given limit becomes, for 0 x tend to 0 minus, we are having this, the limiting value of this part, this thing is minus 2. So we get minus root 2, and so therefore LHL not equals to RHL. This implies limit x tending to 0 e to the power x minus 1, this limit does not exist. Does not exist. This was a little tricky problem, so you have to be very careful. Okay, let's see problem number 7, 8. Problem number 8. It says uh, limit x tending to 2, limit x tending to x minus 2 divided by log a x minus 1. Okay, so we have we know that the standard result uh, x, the general mm, form of the standard result is log a 1 plus fx by fx is log uh, what was the result? The general form was mm, log AE. So log AE, we know this is log AE if we have limit x tends to c fx is coming out to be 0. Over here we can see that uh, we have x minus 1. So when x tending to 2, over the general form is when x tending to c, 1 plus fx is tending to 1 because fx is tending to 0 when x tending to c. So this 1 plus fx is tending to 0. Over here, if x is 2 tending to 2, this x minus 1 is tending to 1. Is tending to 1. Yeah, right. So if over here the general form is this 1 plus fx will tend to 1 because at fx tending to 0 when x tending to c. So this whole thing becomes 1. Over here also the x minus 1 is tending to 1 because x is tending to 2. So uh, uh, we can have we can write how we can write x minus 1 in the form of 1 plus fx. 1 plus x minus 2. So x minus 1 is equals 1 plus x minus 2, and now we see that we have this x minus 2 and also this x minus 2. We can bring the x minus 2 down as the denominator to log a. So this is x tending to 2 1 by log a 1 plus x minus 2 by x minus 2. So we have got the general form, and we can see over here the general form fx is tending to 0 when x tending to c. So over here the fx is x minus 2 which tends to 0 when x tending to 2. So now we can apply the standard result and we get log a e which is equals to log e a. Okay, so this is the answer. Do we have any more problems? 8. No. Okay, this was all the sample problems. I hope you got a decent idea about the problems on logarithmic and exponential functions using the standard result, using these three standard result, uh, but using these three standard result. But always keep in mind that this is the special form, but the general form is like this. Instead of x, we can have a function f(x), and that if that function f(x) at a given limiting value of x is tending to 0, then we will have the same result. So also, if instead of a we have e, then it becomes 1. Also for this standard result, log a 1 plus x by x, x tending to 0, we have log a e. Instead of x, we could have any function f(x), and that f(x) must tending to 0 for the given limiting value of x, tending value of x. So we have these results. Also, the third one is 1 plus x to the power 1 by x equals to 1 when limit x tends to 0. Here also we can have, instead of x, a function f(x), which should tend to 0 at the given tending value of x. So yeah, as usual, I have prepared a DPP sheet uh, on this topic for solving limits of exponential and logarithmic functions using these three standard results. Please solve it in your free time, and I will provide the solution to the DPP in the next 24 hours. And yeah, that is all for this video. Stay tuned for the solution, and more videos will come on the limits, because I have to cover the trigonometric functions and some a standard result on polynomial function like x to the power n minus a to the power n by x minus a limit x tends to 0 is n into a to the power n minus 1. That result along with the expansion series. So for these problems, we have not used the expansion series, but there are lots of good problems, harder problems, where it will become very easy to solve the limit if we use the expansion series results. So yes, thanks for watching. Until the next video, take care and bye.